All right.
Okay. All right. Welcome, everyone. We're going to give this a minute because everybody's been in the waiting room. So until we get stable numbers, but welcome. Thank you for joining us today. So again, if you're just joining us, I'm just waiting for everybody to get from the waiting room into the webinar, just looking at the numbers until they stabilize. So thank you for joining us today. Slowly but surely they're trickling in, Andrea. So I'll get started in a second, but it looks like they're starting to stable out a little bit, which is great. So I'm going to go ahead and just give the intro. So good afternoon, everyone, and welcome to the latest IRIS webinar. This is your host, Danielle Sumi, speaking from her home, but I work for the Incorporated Research Institutions for Seismology, which is headquartered in Washington, D.C. IRIS is a consortium of universities and an NSF-funded science facility that operates programs that enable Earth scientists to perform advanced research in geophysics, particularly in seismology. Webinars are recorded and archived on the IRIS Earthquake Science YouTube channel, which you can just easily find if you go to YouTube, IRIS Earthquake Science. So the webinar ground rules are only the presenter, Dr. Andrea Llenos, and I will speak. If you have a comment or question as the webinar unfolds, then please clearly and concisely type it into the Q&A box on Zoom, not the chat box, the Q&A box, please, on the webinar control panel. At the end, I will read your name and question to the speaker. If similar questions have been asked, I may combine or skip them. If the webinar crashes due to Zoom or internet issues, I will reboot it. Just click on the webinar link again. And in the chat box, so not the Q&A box, but in the chat box, I will place a link to a short 5-minute survey. Your opinions and insight will help us to inform future webinars. One of the questions we'll ask if you are watching this remotely in groups, maybe within your pandemic pod. So if it's more than just you, please let me know. Today's webinar is part of IRIS's continued efforts to provide resources and tools that enable research and professional development. Our presenter today is Dr. Andrea Llenos, who is a research geophysicist at the United States Geological Survey. She recently moved to the Geologic Hazards Science Center in Golden, Colorado, from the Earthquake Science Center in Moffett Field, California. As a statistical seismologist, her research focuses on using statistical methods to characterize earthquake occurrence rates in catalogs for use in both short-term earthquake forecasts as well as longer-term seismic hazard models. She earned Bachelor's of Science degrees in Geology, Physics, Mathematics, and Engineering from Brown University in 2004, and a PhD in Marine Geophysics from the MIT and Woods Hole Oceanographic Institution Joint Program in Oceanography in 2010. She was also a postdoctoral scholar at Stanford University and a Mendenhall postdoctoral fellow at the USGS Earthquake Science Center in Menlo Park, California. So without further ado, here's Dr. Llenos to talk about improving earthquake rate models for seismic hazard forecasts, swarms and fluid injection in volcanoes. Oh my. Thanks, Andrea.
All right, thank you so much, Danielle. And thank you. This talk today is going to focus a lot on sort of the developing earthquake rate models, particularly for probabilistic seismic hazard analysis. And so I'm going to start off by giving a very brief primer on probabilistic seismic hazard analysis, or PSHA, and then go from there to describing the one-year seismic hazard forecasts that the USGS produced for induced and natural seismicity in the central and eastern US. And to sort of give context for sort of the first main part of my talk, which is going to describe a new approach that we've developed for estimating background earthquake rates, specifically for use in PSHA. And then in the second part of my talk, I'm going to be describing a new way to model the rate of caldera collapse earthquakes, and particularly in Kilauea volcano in Hawaii, for inclusion in the upcoming update of the National Seismic Hazard Model for Hawaii, which is going to be released next year. So let me start off by giving sort of a really brief introduction to PSHA. Before I started on this work, I wasn't very familiar with it myself, so I figured, giving a really quick overview of it would be helpful to provide context for the rest of this talk. So there are, basically three main steps in probabilistic seismic hazard analysis, which you can see in this figure here. And the first is developing a model for the earthquake source, seismicity sources. And this is basically where you expect earthquakes to occur in the future. And this can come from known faults in the region or spatially smooth background seismicity off faults. The second part of the model is a recurrence model. So basically, how often are these earthquakes expected to occur? And you can develop this by looking at the magnitude frequency distribution of the earthquakes in the region, as well as the Poisson rate of independent earthquakes. And so this is basically the rate of earthquakes you get after you decluster the earthquake catalog you're working with, which means that you remove aftershocks and forecasts primarily. And so presumably what you're left with is going to be the rate of main shocks that's representative of the long-term rate of earthquakes in the region. And then the third part of PSHA is the ground motion model. So basically, how much shaking are these earthquakes likely to cause? And this is estimated using typically empirical ground motion prediction equations. In this talk, I'm primarily going to focus on these first two steps, basically developing the earthquake source, and earthquake recurrence or earthquake rate model. Basically, ground motion models are whole separate talk. And so the end results are hazard curves and maps, which are shown here. So hazard in this context is going to be the probability of exceeding various levels of shaking over the specific long-term time windows, over 50 years, for example. And so this is just a cartoon illustrating how these hazard curves look. We have a probability of exceedance on the y-axis, and then on the x-axis is your specific ground motion parameter. And this could include things like peak ground acceleration, or PGA, or spectral acceleration of various periods, at various periods. And so the things I want to emphasize here are that basically the earthquake rates that are used in PSHA are again expected to be a Poisson rate, often assumed to be a Poisson rate of independent earthquakes that you derive from a declustered catalog. And then again, these PSHA is done over a specific forecast time window, and typically it's over 50 years. So this is an example constructed by taking multiple hazard curves at multiple locations and then identifying the probability threshold of interest. So typically this is something like 2% in 50 years. And so once you take, you can just basically read off those values at all the different locations, and you can come up with a map. And so this is a 2014 USGS National Seismic Hazard Model. This is the last time the NSHM was updated for the conterminous US. And so this map is showing the colors indicate the peak ground acceleration. So it's a fraction of gravity that has a 2% probability of being exceeded in the next 50 years. So you can see the obvious high areas of high seismic hazard are California here on the West Coast, as well as, for example, the New Madrid fault zone here in central US. So the other thing to note here are these black picks, or suspected induced seismicity, were deleted from the catalog that was used to produce this hazard model. And the reason for doing this was because induced seismicity, sort of by its character, is very short term. So it wasn't expected to really affect the hazard over a 50-year time window. And a lot of times induced seismicity tended to be smaller in magnitude. And so again, that's, and we didn't really have a good way to deal with its sort of ephemeral nature. And so they were some induced earthquakes, suspected induced earthquakes were pretty much just removed from from the 2014 map in these areas. So that raises the question of, particularly starting in 2009, how to deal with these areas of induced seismicity in our seismic hazard models. Because starting in 2009, as pretty much we all know by now, the earthquakes in the central and eastern US started to time from 1975 to 2019. And you can see it really starts to ramp up in late 2009 and 2010, subsequently decreasing since then, but it's still at a level that's a background level that's higher than it was prior to 2009. So induced seismicity presents several challenges to sort of this the standard PSHA framework. So this becomes difficult in the case of induced seismicity because it's really difficult to predict future field operations. And so where things like wastewater fluid injection is going to be occurring, or oil and gas production is going to be occurring that might trigger future earthquakes. And in terms of how often they're expected to occur, again, because these induced earthquakes are largely driven by human industrial timescales on the order of days to weeks to months instead of sort of the long-term rates that are currently being used in PSHA. And then they could, at the time that we started putting these maps together, there were a lot of questions regarding their magnitude distributions, how much clustering occurred in them, and what the potential maximum magnitude might be. And then there are similar questions regarding the ground motion model, different ground motion models than natural earthquakes. And so all of these challenges led the USGS to try to address these challenges. The USGS produced, starting in 2016, these one-year seismic hazard forecasts for the central and eastern US. And so this just shows the open file report 2017, and the last one and so the basic way that these maps were put together, and one thing of course to note is that these are one-year forecasts rather than the 50-year forecasts that for example, the 2014 NSHM was. And this was intended to deal with the fact that, again, these earthquake rates were changing on such much shorter time scales than 50 years.
Andrea?
Yes?
Hey, sorry to interrupt, but it seems like your internet's coming in and out. So the audio isn't as clear. I don't know if there's anything that you can do on your end to rectify that or not, but.
I will try, hold on.
Okay, thanks. I know it's difficult since we're all working from home.
Yes, and I would normally be giving this talk is much closer to Wi-Fi, but so if it continues to be a problem, let me know, and I will definitely shift downstairs and see if that improves things.
Yeah, so someone also said you could also call in and just use the video and then call in.
Okay. Let me try to do that.
Okay.
Sorry, folks.
No, it's okay. I mean, yeah, that's another thing that you could do, Andrea, is just try to cut video.
Okay.
Because that might help with the bandwidth. Yeah, that might help with the bandwidth.
All right, great. Let's try that for now.
Okay, and, yeah.
Yeah, definitely let me know if it doesn't solve the problem.
Okay, thanks.
Okay, sorry about that. So as I was saying, basically these maps were produced, well, first a set of induced seismicity zones were identified based on the scientific literature, as well as in consultation with local geologists and other experts. And so you can see these zones highlighted here, particularly Oklahoma and Kansas. some parts of Texas, Colorado and Arkansas, and so on. Okay, and so the way that these hazard maps are constructed, basically a logic tree is used to identify various, to lay out various various model parameters and decision choices for those parameters. And then those different choices are assigned different weights. And so this just illustrates the logic tree that was used for these induced seismicity zones for these maps. So you can see sort of the top level is the earthquake catalog and fault sources and area sources. There's a level dealing with how the earthquakes are classified, how long of the time window we're using to estimate the earthquake rates, smoothing distance, and so on. So these top models deal with specifically, the top levels deal specifically with the earthquake rate model, and the bottom one is dealing with the ground motion model. So that's just an example of the kinds of logic trees that are used to make these hazard maps. So this is illustrating the 2018 seismic hazard forecast for the central and eastern US. So the colors here are indicating the chances of potentially minor damage ground shaking in 2018, ranging from less than 1% all the way to 10 to 14%. And you can see that the highest hazard is pretty much occurring here in Oklahoma. And then you can also compare that to sort of the results from the 2014 National Seismic Hazard Model here in the Western US. And you can see that the hazard at this point is pretty much can be comparable to what's seen in California. Okay, so as we were going through this exercise of putting these shorter term hazard forecasts together, we started to discover some issues, particularly regarding the use of declustering in PDCJ. So as I mentioned before, declustering is basically removing aftershocks and foreshocks from the earthquake catalog so that what's left is presumably representative of the long-term background earthquake rate in the region. And so again, the main purposes for declustering are to achieve a Poissonian or an independent background earthquake rate, and also to prevent aftershocks from biasing sort of the expected long-term spatial distribution of main shocks in the region. And so we just cluster a catalog and then spatially smooth that declustered catalog to produce maps of the forecasted earthquake rate. So the trouble with this is that declustering is a very non-unique problem. And there are many different approaches, many different methods to decluster a catalog. And these declustered rates, these estimated background rates, can vary widely depending on what method you use. And another issue is that most applications don't really objectively optimize parameters for the region of interest or consider uncertainties. So for the USGS NSHM, typically the method that's used is a window-based Gardner-Knopf GK74 method, which is where earthquakes that are within a particular space time window around a specific magnitude main shock are removed. The thing is, the Gardner-Knopf, those windows were tuned to California seismicity, seismicity in Central California. And so you wouldn't necessarily expect those aftershock windows to apply to the central and eastern US, which is of course a completely different tectonic region. And so this suggests that basically declustering is a currently unmodeled source of uncertainty in our hazard assessments. The other thing that we noticed, especially as we compared the hazard maps that were produced for 2016, 2017, and 2018, is that the GK74 declustering actually led to counterintuitive results as we move through time. So if you'll recall from sort of the slide I showed towards the beginning that showed the increase in earthquake rates, I mentioned that the seismicity rate in the central and eastern US had been decreasing since 2015. But you can see as you look at the forecasts going through the years, and these are all using the same color scale, the seismic hazard actually increased in 2018, even though the full seismicity rate decreased. And so this was very counterintuitive because everybody was expecting the seismic hazard to actually decrease. And this was largely due to the declustering that was done. So to address some of these issues, I and Andy Michael developed a new approach towards estimating these background earthquake rates, which we call the regionally optimized background earthquake rates from ETOS method, or the Robert method, for probabilistic seismic hazard assessment. And this was published earlier this year in BSSA. So another issue with declustering, particularly for PSHA, is that it can affect the Gutenberg-Richter B value. And this is a very critical parameter for PSHA because it's, of course, what's used to extrapolate the earthquake rates from the much more commonly observed lower magnitude earthquakes to the rarer but more consequential higher magnitude earthquakes. And so if we look at this magnitude frequency distribution from Oklahoma and southern Kansas in 2016, the black dots here basically show the distribution from the full catalog, and we ended up having a B value of about 1.5. And then the magenta dots here, magenta squares here, sorry, is the MFD from a Gardner-Knopf declustered catalog. And you can see that this is a much lower B value of 0.88. And you can also see that sort of the extrapolated rate actually crosses over the rate, the rate extrapolated from the full catalog, leading to a higher predicted rates at larger magnitudes. And so this implies that aftershocks have a higher B value than main shocks, which may or may not be physically plausible. So in the Robert method, instead of being a window-based method like Gardner-Knopf, basically, here are the steps of the algorithm. So we start off by selecting an earthquake catalog for the specific region and time period of interest. And this is, presumably with similar seismic tectonic behavior and data quality. So basically data completeness. And from this catalog, we can determine the B value, and then we estimate ETOS parameters using maximum likelihood estimation. So ETOS stands for the epidemic type aftershock sequence model. It's a stochastic seismicity rate model that's commonly used in aftershock forecasting, for example. And so the main equation here is shown here. And basically in the ETOS model, the seismicity rate at some time t in a region is equal to a background rate mu plus the summation of the aftershock rates that are triggered by all of the earthquakes that occur in that region prior to time t. This aftershock rate is characterized by productivity parameters k and alpha, as well as the Omori decay parameters c and p. So we can estimate those parameters for the catalog using, again, maximum likelihood estimation. And with those parameters and then the B value, we can simulate a seismicity catalog of similar duration as what was observed. And from that simulated catalog, we determine a new B value and new ETOS parameters. And then we can do stochastic declustering with these new parameters to decluster the observed catalog. And the main equation for stochastic declustering is shown here. So this is basically the probability of an earthquake in the catalog being a triggered earthquake from some other event in the catalog. So the probability of it being an aftershock of something. And basically, if you just take 1 minus that, that gives you the probability of an earthquake being a background earthquake. And so using those probabilities, we can produce a one instance of a declustered, stochastic declustered catalog for this region. And from that catalog, we can compute the spatially smooth earthquake rate model, such as the one shown here in Oklahoma. Again, because this is a stochastic declustering method, then this produces just one possible declustered catalog. We can loop over these steps to produce a suite of our potential declustered catalogs, and are in this, I think this study was something like 10,000. And so this is just showing the distribution of sizes of those declustered catalogs now from those different R models. And we can take the mean from that suite of models and use that to produce the Gutenberg-Richter A value or earthquake rate grids that are the input to PSHA calculations. So basically, we like this method because, for one thing, parameters are being optimized for the region of interest. So we're not simply relying on windows that were tuned to California seismicity. This also gives us the ability to include uncertainties in those parameters using this, this simulation approach that was first developed by Wong and others in 2010. And then the B value ends up not being significantly biased, as we saw for the Gardner-Knopf method, because in the ETOS framework, aftershocks and main shocks end up having the same B So we tested our method in two different regions. One was Oklahoma and Kansas, which of course is primarily induced seismicity. And then the second was the San Francisco Bay Area, which of course is natural tectonic seismicity. And then we compared our new method against some of the more standard declustering methods, including the one I mentioned before, Gardner-Knopf, which is a window-based method. In Oklahoma, we also tried a modified version of Gardner-Knopf, where that was developed by Rawson and others in 2019, where the spatial windows were actually tuned specifically to Oklahoma seismicity, although the temporal windows ended up being the same as the original Gardner-Knopf method. We also looked at another commonly used declustering method, which is the Riesenberg R85 method. This is a link-based method where clusters are identified using spatial and temporal interaction zones. And then the more recently developed nearest neighbor method of Zalyapin and others, as well as sort of a more single instance of a stochastic clustering method, which only uses the ETAS MLE parameters rather than looping over multiple parameter sets as we do. So here's some of the results for Oklahoma. Again, this is just the year 2016, magnitude 3 and higher earthquakes. This figure here on the right shows the yearly number of earthquakes from 2012, just to, again, illustrate what some of the issues were with the seismic hazard forecast. The black shows the full catalog rates. The different symbols here are from the different declustering methods. And you'll note that for the Gardner-Knopf method, the magenta squares here, you can see that the earthquake rate the cluster rate has been increasing steadily since 2012. And this is what ended up causing the seismic hazard to increase from 2016, 2017 to 2018. Whereas all the other methods, as well as the full catalog, you can see that, again, the rates have been decreasing since 2015. The figure here on the left basically, again, shows the cumulative distribution function of the number of earthquakes in the different declustered catalogs that were produced by the Robert method, and the mean of those catalogs is shown by the vertical black line here. And the other different lines indicate the sizes of the declustered catalogs from the other declustering methods. And then on the bottom right is just showing the cumulative number of earthquakes in 2016, again, with the different declustering methods compared to the full catalog. And so the main thing to note here is that you can see that there's a great amount of variability in terms of the size or the size of declustered catalog you get, depending on what declustering method you use. So this figure shows the smooth seismicity rate maps from the different we get using the different declustering methods, going from Gardner-Knopf here on the left, the GKOK, so the modified Gardner-Knopf method in the center, Riesenberg, nearest neighbor, ETAS, MLE, and then our Robert method down here. And also in each of these maps, I'm showing the number of earthquakes, so the size of each of the declustered catalogs. So right away, you'll notice that Gardner-Knopf removes a lot more seismicity than the other methods do. You can see that about a little over 100 earthquakes are left after declustering is done, compared to 300 to 700 earthquakes in the other methods. And then these are all in the same same color scale. These are showing number of earthquakes in each grid cell. And you can see that there's also a different spatial distribution as well. So these are the hazard maps you get when you input those earthquake rate maps. And these are showing the peak ground accelerations in colors that have a 1% chance of being exceeded in 1 year. And so also in each of these panels, I'm showing the B value that you get in each of the declustered catalogs. And again, we're seeing a much lower B value in the Gardner-Knopf declustered catalog than we're seeing in any of the other declustered catalogs. And just as a reminder, the B value of the full catalog was about 1.5. And so it's this very low B value that makes the hazard jump up so significantly in this region. Because again, the slope is becoming, the slope of the magnitude frequency distribution has changed significantly. And so that's causing the larger, a higher expected rate of larger magnitudes than you would get with a higher B value. So you can clearly see that Gardner-Knopf sticks out as being significantly different from all the other hazard maps. And then, of course, the other thing that we're interested in looking at is the spatial distribution of main shocks, because again, one of the purposes of declustering was to remove the spatial bias due to aftershocks, so that you have sort of a PDF representing the expected locations of main shocks into the future. And so here again, you can see that Gardner-Knopf has so basically, these are just the earthquake rate maps that I showed before, except they're normalized by the size of each catalog to really emphasize the spatial PDF. And you can see that, again, Gardner-Knopf has a much different character than any of the other declustering methods. The other declustering methods typically have, you can see like 4 or 5 peaks in the distribution, but they do vary in terms of which of those peaks become more significant. So for example, the ETOS-based methods down here, you can see that the largest peak is here to the west, as opposed to sort of more evenly distributed peaks for the other methods. So to summarize the Oklahoma results, we found that GK74 has the lowest rates but the highest hazard, again, due to the really low B value that we got from that declustered catalog. The GK-OK method with the different spatial windows mitigates this effect to some extent, but you can see that the B value is still slightly lower than the B value from the other methods. Riesenberg had the second highest hazard with the highest rates and a B value close to the full catalog B value. And then the other methods resulted in relatively similar hazard maps, but the full hazard curves, which I didn't show here, but are in the paper, differed between the different methods. And then the spatial distribution of main shocks also, while they were broadly similar, they varied in detail among the different methods. So just really quickly to show the results for San Francisco Bay Area, again, this is now just to show that the effects that we were seeing in Oklahoma weren't simply due to the fact that we were looking at induced seismicity. And so again, the yearly number of events are shown here with the full catalog in black compared to the different declustering methods. Again, you can see that there's a lot of variability in the size of the declustered catalog. So basically the estimated background rates you get depending on what declustering method you use. And so here are the Bay Area rate maps. Again, we have Gardner-Knopf here to the left. You can see that again, this is resulting in the most earthquakes being declustered from the catalog. So it's the smallest, so as the smallest earthquake rate per year. Riesenberg, nearest neighbor, and then the 2 ETOS on the lead, and then our Robert method here. The interesting thing to note is that you'll see that there's this bright spot here that remains in the Robert method, and this is actually due to the 2016 San Ramon swarm. In the ETOS model, swarms appear as increases in previous work that we've done has shown that swarms manifest themselves as increases in the background earthquake rate. And so that's why this is, and so that's why the swarm doesn't end up being declustered here, and it still shows up in these background earthquake rate maps. So these are the hazard maps we get from those earthquake rate maps. And you can see that, again, we're getting the highest hazard here from Gardner-Knopf because we have because the B value is, again, being decreased relative to the other B values and the B value of the full catalog. So while they're the same, pretty much 4 or so peaks in the hazard, it definitely has much higher hazard here in these two southernmost areas. And then here's the spatial distribution of main shocks. Again, these are just normalized earthquake rate maps, where again you can see that Gardner-Knopf is kind of different, looks kind of different from the other methods, and so this really suggests that the effects that we're seeing from the different clustering isn't just due to induced seismicity. So to summarize the Bay Area results, again, we found that Gardner-Knopf had the lowest rates but the highest hazard because of this B value reduction. Again, Riesenberg had the second highest hazard. The other methods resulted in fairly similar hazard, but there's still some variability in the spatial distribution of main shocks. But so this suggested that this isn't due simply to induced seismicity, but at least it wasn't as extreme as we observed in Oklahoma and Kansas. All right, so to summarize this first part of the talk, earthquake rate models are critical parts of hazard assessments because they're what's used to forecast the seismicity rate into the future. But we found that these earthquake rate estimates can vary depending on the declustering method that's used to compute the seismicity rate model. We prefer we think that the Robert method offers some advantages over some of the other methods because it objectively optimizes parameters for the region of interest. It includes uncertainty in those parameters, and it preserves the B value from the original catalog. But we do need to do some further work because the results that I showed, basically they were hazard maps computed over relatively short time windows, so 1 year. In the Bay Area, we were looking at sort of I think 5 years. And so we need some further work to determine how to apply Robert over much longer time periods. And because over those longer time periods, the earthquake catalog quality is going to vary quite a bit. And so we have to determine how we can deal with sort of those differences in catalog quality and completeness. All right, so for the last part of this talk, I'm going to shift gears a bit and talk about a recent study that we've been doing to develop again augment a seismic hazard model, and that's modeling the rate of magnitude 4 and 5 caldera collapse events in Kilauea in Hawaii. So as we're pretty much all familiar, so there was a big eruption in Kilauea in 2018, and during which portion of the caldera collapsed. So this figure from Neal et al. Just shows the caldera with the approximate outline of Halemaumau crater before the eruption happened. And so I was going to show a video. I don't know how this is going to work. I think it should still work. Let's see.
Andrea, I'll let you know when it comes up. And your audio has been sounding great, so thank you.
Okay, perfect. Whoops. I'm just going to stop sharing for a minute so I can select a different screen to share. All right.
Looks great.
Perfect. Okay, so this video is basically just a time-lapse movie of basically daily images that were captured from the Hawaii Volcano Observatory, which is located on the rim of the caldera. And so it starts basically when the eruption started in April of 2018. And so let's just play this. And you can see by May that the caldera has started to subside a bit. And it's not until late May, early June that you can really see the dramatic subsidence that starts to occur. And then the eruption ended sometime in August. So all of this subsidence didn't really occur in sort of one continuous collapse. It occurred in a series of almost daily sort of drop downs of the caldera. So if I kind of, just just go through frame by frame, you can kind of see the change that occurs sort of day by day. And so during each of these days, this drop down resulted in magnitude 5 or so earthquake, caldera collapse earthquake being produced. So let me switch back to my slides. Okay. All right, so during the course of the eruption, about 62 of these caldera collapse earthquakes, so these daily drop down events, occurred. This is just showing the magnitude time history of the earthquakes in the caldera during the eruption. And you can see that these collapse events occur fairly regularly. And again, they're pretty much have similar magnitudes ranging from about 4.7 to about 5.4. And so these earthquakes were deficient in, well, they had a very long period signals and were deficient in high frequency energy, but they still ended up causing quite a bit of damage to particularly to the Hawaii Volcano Observatory, or HVO, which, as I mentioned, is on the rim of the caldera. So these photos here just show some of the damage that occurred at HVO. You can see some of these cracks in the floor and the walls. And again, this is just comparing what the caldera looked like at the start of the eruption to what it looked like after the caldera collapsed. And so this shows that these 62, the seismicity that occurred during the caldera collapse can pose a significant seismic hazard, even though the earthquakes aren't very large. And particularly, it can pose a hazard to buildings and infrastructure that's located around the caldera. And so this is a source of seismic hazard that really should be accounted for in a seismic hazard model. So the USGS is actually updating, in the midst of updating the Hawaii seismic hazard model. And again, I think as I mentioned at the beginning of this talk, it's to be released next year. And so the NSHM for Hawaii, this updated model is going to include updated earthquake data, some updated methods, and as well as the seismic hazard due to these caldera collapses for the first time. So to determine the seismic hazard that's due to caldera collapses, we need to know or be able to estimate what the expected rate of collapse earthquakes are over the next 50 years, because this is going to be a 50-year seismic hazard forecast. And in order to estimate that, we need to have some estimates for the rate of caldera collapses that we can expect, as well as the rate of magnitude 5-ish earthquakes that occur per collapse. So to try and develop a model for that first part, the rate of collapses to expect, we used some resources provided by HVO. So this is, for example, a simplified table of the historical activity at Kilauea. And so from that table, we found that there were 6 summit subsidence events at Kilauea that included earthquakes within the caldera since 1906. And so we basically did that by comparing the subsidence events, which are shown here in this figure on the right, indicated by stars, this timeline of activity at Kilauea. We compared those events to the earthquake catalog that's being used to produce the seismic hazard model. And so that's how we settled on these 6 summit subsidence events. And we term these caldera collapses. So that's what I'm going to be referring to when I say caldera collapses for the rest of this talk. So to determine the other part that we need to figure out, the rate of earthquakes per collapse, what we did was tabulate the number of earthquakes produced by each of those 6 collapses. And so that's what's shown here in this table. The years of the 6 collapses are shown here, as well as their estimated subsidence volume or collapse volume, and then the number of earthquakes that can be associated, that occurred in the caldera during each of those collapses. So you can see that clearly the most earthquakes were triggered during the 2018 collapse, although 1924 also resulted in a large number of earthquakes. So we can actually model those earthquake counts using a negative binomial distribution. And we use this distribution because it's a discrete distribution. It's often used to model earthquake clustering, because unlike the Poisson distribution, it provides a way to model count data where the mean and variance are necessarily equal. And so the fit of the negative binomial distribution is shown here on the right by the red line, and the observed counts, magnitude 4 counts, are shown by these bars. And obviously this is an incredibly small data set. So the fit is probably not particularly well constrained, but at the very least, it doesn't look like it's an outrageously wrong fit. And so we can just proceed using this model and adapt as necessary as we learn, as we gather more data in the future. Okay, so now that we have models for the collapse rate and the rate of earthquakes that occurred during the collapse, we can combine those 2 distributions. So Again, we're modeling the number of collapses in 50 years as a Poisson distribution. And when you take those 6 collapses that we identified over the last 100 and some years, that results in a Poisson rate of about 2.6 per 50 years. And then we're going to be modeling the number of events in each collapse, again, using this negative binomial distribution. So it turns out that you can combine those distributions analytically and then compute it recursively. I don't have time to go into the details now, but there are basically 4 model parameters that are involved in this combined model. And one is the Poisson rate parameter, which is, again, the number of collapses to expect in 50 years, R and P, which are parameters for the negative binomial distribution, and then this parameter Nmax, which is the maximum number of events per collapse based on, and we estimate this parameter based on magma chamber geometry and depth, and use it to truncate the negative binomial distribution. And so just to quickly show how we're estimating or trying to constrain Nmax, one can argue that there should basically be an upper limit to the number of earthquakes, number of drop downs basically that can occur. At some point, you're going to hit the top of the magma chamber. So we estimate sort of a maximum volume of collapse using a cross-sectional area of the magma chamber that was estimated from geodetic data by Anderson and others. And then comparing, that results in sort of a rough estimate of 2.2 kilometers cubed. And the total volume of the 2018 collapse was about 0.8 kilometers cubed. And if we assume a relationship between the volume of collapse and the number of collapse events, ultimately that results in showing that the 2018 collapse volume was about 40% of the maximum volume you might be able to expect, and triggered 85 events. And so we can use that to sort of extrapolate that a maximum volume collapse could trigger up to 300 of these collapse earthquakes. And so this is obviously rather hand-arm wavy. There's not a huge amount of constraints here on this calculation, but we did do a sensitivity study, and it turns out that the results aren't actually very sensitive to this parameter. So we use this sort of preferred, this number 300 is sort of our preferred Nmax for now. And again, this is something that can be easily adjusted in the future. All right, so our preferred parameter values are shown here in the red. Again, we have a rate of 2.6 collapses per 50 years. We have parameters characterizing the negative binomial distribution for the number of events per collapse, and then this Nmax parameter. And then we can do simulations to account for uncertainty in those parameters. Again, we're modeling lambda as a Poisson variable. We model the negative binomial parameters as bivariate normals using maximum likelihood estimates and covariances. And then Nmax, we're just going to model as a uniform variable between 200 and 400. And so we can basically we basically look at 100 or 1,000 randomly drawn parameter sets using these distributions to account for uncertainties. So here are the results. This is a cumulative distribution function showing the expected rate of magnitude 4 and up collapse events. And so the thin gray lines here just show the different parameter sets. And then our preferred model is shown by the blue line here. The mean of the different parameter sets is shown by the green line with the plus or minus 1 sigma. The median is by the green dotted line. And then the red line here is showing the Poisson distribution that has the same mean number of events as our preferred model. And so you can see that that has a very different character than than our model does. And then the vertical black line here is showing the number of earthquakes, collapse earthquakes that were actually observed in the last 50 years, which is I think something like 84. And so this table sort of summarizes some basic statistics of the different models. And then this final column here shows the probability for each of those models of observing the number of events that was actually observed in the last 50 years, given the model. And so basically for our preferred model, you can see that there's a 14% chance that we would have observed the 84 events in this model. Similarly, for the mean and the median models, that's something like around 12%. But again, for the Poisson model, you can see that this is very different. Then that probability is something very close to 0. So that means that what we actually observed during the 2018 eruption would have been extremely unlikely using a simple Poisson distribution. And again, as I've mentioned sort of throughout, the Poisson distribution is what's often assumed for PSHA. We can go through a similar exercise for the magnitude 5 and higher events, which are the earthquakes of more interest and more impact for PSHA. The different parameters are shown here. And here are the results. Again, as you might expect, the distributions are now shifted to the left because you would expect fewer earthquakes than magnitude 4 earthquakes, collapse earthquakes than magnitude 4 earthquakes. And then again, you can see that the Poisson distribution is again very different from the other models, and again results in what was actually observed being incredibly unlikely. So now that we have those distributions for the rate of collapse events, we can combine those with the ground motion model for collapse events to estimate the hazard. And so this is just showing a spectrum, median ground motion on the vertical axis and the period on the horizontal axis. The different lines are the different ground motion models that have been tested in Hawaii. And you can see that, and so the brown line here is actually Gale Atkinson's Hawaii specific ground motion model, but modified to account for caldera collapse events because, as I mentioned before, these collapse earthquakes have reduced ground motion at short periods. So basically, which you can see here. And so here's the hazard curve you get when you combine that ground motion model with our rate model. This is again, so this is showing the probability of exceedance for 50 years versus acceleration, ground acceleration. And so the black line is just the Poisson. Well, so the red line is what you get using our clustered collapse model with plus or minus 1 sigma. The black line is what you get with a Poisson distribution with the same mean as our clustered collapse model. And then these different dotted horizontal lines are different probabilities, probability thresholds of interest. So basically the 2% and 50-year threshold and the 10% and then 10% 50 years. So again, the Poisson model is what's typically used for PSHA. And if you look at the sort of the 10% or less, 10%, 2% probabilities, you can see that actually, the Poisson model does a reasonable job at matching the clustered collapse model at these lower probabilities. But it ends up overestimating the ground motions at higher probabilities. So that's definitely something to keep in mind as we start considering, as we consider different hazard products and start looking at different time periods and different probabilities of interest. And then here's the hazard map that results. So here on the left, these are basically just showing the mean hazard at 2% in 50 years for 0.2 second spectral acceleration and then 1 second spectral acceleration. And here on the left is the total hazard for Hawaii. And on the right is just showing the caldera collapse model, hazard due only to the caldera collapse model. So you can see that really, as you might expect, the caldera collapse hazard really is an issue close to the Kilauea caldera. But as the images I showed at the beginning of the section suggest, we can't ignore the contribution of those events to the hazard because they obviously are capable of causing damage to structures and infrastructure around the volcano. So, at least we now have a way to incorporate these kinds of events into our seismic hazard models. So Andy and I are continuing to work on this type of combined clustered collapse model because it could have applications for other kinds of clustering behavior in PSHA. So for example, aftershocks. In our clustered collapse model, you'll recall that we had two distributions that we combined together. One was a Poisson distribution for sort of a driving process, and the other was a distribution describing the response of the earthquakes to that process. And this is very similar to main shocks and aftershocks, for example. Main shocks can be represented as sort of the driving process, and then aftershocks are a response to that process. And so one of the things we're exploring is how we can generalize this model for other applications. And as I said before, accounting for clustering is going to be more important as we move towards shorter forecast windows, such as one-year forecast windows that were produced in Central and Eastern US, and or higher probabilities of interest. And I will simply note that if you're interested in this kind of thing, Andy and I are actually co-convening a session in SSA next year called Beyond Poisson, Seismic Hazards and Risk Assessment for the Real Earth, where we're inviting presentations that explore this topic further. Okay, so before I wrap things up, I just want to talk a little bit about sort of the broader impacts of my work. I really love what I've been able to do with the USGS, working at the USGS, because primarily because of the public service aspect of it. And the fact that the research I do has a lot of direct impact on highly visible products, such as the National Seismic Hazard Models, which of course inform building code throughout the US. It is also used by the insurance industry to help set insurance premiums and develop risk models. And then I've also been fortunate to work on the aftershock forecasting team. And this is another, which also produces high impact products such as earthquake forecasts following swarms in California. This is just an example showing the recent earthquake forecast that we released for the Westmoreland swarm in Southern California that happened at the end of last September, beginning of October. And so I really appreciate being able to work on these kinds of products that really have an impact that really can be accessed by the public. But the other thing I also want to mention is some of the other things I've been involved with that are related to sort of more public outreach, education and outreach. And one of them is attending the National Diversity in STEM conference that is organized by SACNAS, which is the Society for the Advancement of Chicanos, Hispanics, and Native Americans in Science. And so every year they hold a National Diversity in STEM conference. And for the past 5 to 10 years or so, 10 to 15 years or so, the USGS has been sending a contingent of scientists and other personnel to attend the conference and to talk to students, early career professional, grad students, undergrad students, early career scientists about the USGS. In particular, well, I've been fortunate enough to be able to attend 4 or 5 of these conferences over the past 5 years. And it provides a lot of opportunities for one-on-one mentoring, to talk to students about the USGS, about pursuing different careers in STEM and geoscience. As a Mendenhall, as someone who started at the USGS as a Mendenhall postdoc fellow, I also talked to graduate students about that program and about my own pathway through to and through the USGS. And so, so that's something I've really enjoyed being able to participate in over the past few years or so. And this year, of course, the conference was entirely virtual, but it also provided a lot of opportunities to talk to students and for the students to ask questions of scientists and other personnel. And then the other opportunity I've been involved with over the last 6 years has been Letters to a Pre-Scientist, which is a group whose mission is to shown here. It's basically to facilitate one-on-one connections, to humanize STEM professionals, demystify STEM career pathways, and inspire all students to explore a future in STEM. And so the idea behind this group is that so students who are typically from, I think, 5th to 10th grade science students are connected with students in sort of low-income schools and low-income communities are connected with STEM professionals. And over the course of a school year, each student is paired up with a single professional, and they exchange about 8 or so letters. And these letters have different themes. So for example, describing your career pathway, describing times when you had to overcome an obstacle in your personal life or your career, describing how went to how your experiences in college and so on. And so I've really enjoyed participating in this program and just exchanging letters with these kids who ask so many questions, and you learn so many details. And it's really a way to show that really, scientists do all sorts of things, and we're not just the stereotypical white man with a lab coat locked up in a lab somewhere putting chemicals together. There are a lot of different ways to do science and a lot of pathways into science, and that's one thing I always try to highlight in my letters to these students. So that's a program that I really have had a lot of fun with, and I highly encourage anyone who's interested to look into it themselves. All right, so to wrap things up, basically, there's increasing awareness and interest in improving PSHA to account for time-varying earthquake rates. So, for example, due to aftershocks, due to earthquake swarms, fluid injection, or volcanic activity. And some of those ways I've talked about here, and that includes things like improving declustering, or basically improving the way that we estimate these background earthquake rates, and also accounting for uncertainties in those rates in PSHA. Other things that I did not have time to talk about, but that we're also thinking of working on are ways to make hazard estimates based on full or non-declustered catalogs. And then also developing ways to include, where possible, external data. So for example, fluid injection in the case of induced seismicity. And so these avenues of exploration are going to continue to be explored during ongoing work at the USGS. As I mentioned, we're updating the Hawaii NSHM in 2021, the Alaska NSHM in 2022, and then a full update of the full conterminous US in 2023. So with that, thank you very much for your attention. I'd be happy to take any questions, and you can also feel free to email me at the address shown here. So thank you.
Thanks so much, Andrea. Great. Okay, first question is from Alberto Venegas, and he says, thanks for your presentation. I enjoyed it very much and helped understand the science behind the many methods for declustering. I have two main questions. One, following the broader impact you mentioned, the NSHM does not show Puerto Rico. Are there plans to update the currently outdated version for Puerto Rico? And then second, also, could you briefly discuss the forecast for the Puerto Rico January 7th sequence, beginning from early on in the sequence back in January and February to the different iterations you guys have gone through to fit the atypical sequence that developed? So I don't know if you want to take that away.
Sure, yeah. So yes, there is, well, I won't say a plan just yet to update Puerto Rico, but it is being discussed, particularly as it has been a while since it's been updated in light of the recent seismicity. Not clear yet when that update is going to happen. And then in terms of the second question, which was regarding, I guess, the aftershock forecasts that were produced in Puerto Rico.
Yes.
Yeah, so I have not been directly involved in making those forecasts, but they were put out shortly after the sequence. Well, the I guess main shock occurred. And they've been, I believe that they're being updated. Well, I mean, so they're, I mean, basically the aftershocks are still continuing. And in fact, the last, I believe, I forget how large the most recent earthquake occurred was, but that's still considered as part of the aftershock sequence from the main shock earlier this year. And so the activity is still going on. I don't know how often the forecasts are being updated currently. But I mean, it's definitely something that we're still keeping an eye on.
Great, thanks. David Hazel asks, what, if any, consideration is being given to including different declustering methods as a branch in the source logic tree in the future?
That is definitely something that we're considering. In fact, in the Hawaii seismic hazard model, we're now considering, we now have 2 logic branches dealing with 2 that include 2 different declustering methods, the Riesenberg method and the nearest neighbor method. And so as we move on to Alaska and the rest of the US, we're also going to consider using multiple, having multiple logic tree branches to account for multiple declustering methods.
Great, thank you so much. So those were the only 2 questions that we had, but thank you so much for your presentation, Andrea. Thank you for everyone who attended. I know it's a very busy time of year with AGU posters and presentations due tomorrow, but there's a lot of comments that just are saying thank you, Andrea. So because of AGU and the holidays, we are taking a hiatus until 2021, but please join us for our next webinar that will take place on January 28th, 2021, and will be given by Dr. Christina Keating at Rutgers University, Newark. So please join us then. Thank you so much, Andrea, and thank you everyone for attending, and have a great rest of your day. All right, take care.
Thank you very much.
All right, bye.